Good morning and welcome to my presentation. My name is Gabriel Guillet. I am PhD student at Aix-Marseille University in France. And in this presentation, I will talk about my current work, the standard test of a Scheffler type cooker for use by a restaurant. This work is supervised by Benjamin Kadoch, Thomas Fasquelle, and Séverine Barbosa. We thank the region Provence-Alpes-Côte d'Azur, the restaurant Le Présage, and the Institute of Mechanics and Engineering of Aix-Marseille University for their fundings. To begin with, let's go back together to the 1980s. At this time, a German engineer called Wolfgang Scheffler was working on the design of a new reflector with the aim to give a simple, robust, economical, and clean concentrating type cooker to the third world. Indeed, standard parabolas are suffering of a defect. They are not able to keep focusing at the same place all along the year without being relocated. That is a big problem for a community kitchen powered by solar energy. The kitchen cannot be moved, and neither are parabolas because they are often big and heavy. But Mr. Scheffler succeeded. A regular setting of the inclination and curvature of his new flexible parabola allowed him to keep focusing sunlight on the same point all along the year without having to move the structure of the parabola. The moderate price for this innovation was a slightly lower concentration rate. The system gradually spread itself around the world for cooking, but also for many other applications like extracting essential oils. Scheffler reflectors have been particularly successful in India, where they power canteens of some schools, temples, and companies. In this kind of system, Scheffler reflectors are used to produce steam, which is transmitted to the kitchen thanks to pipes. Although the Scheffler reflector has been studied, its combination with a secondary reflector and a cooktop has not. That's why we are happy to collaborate with the restaurant Le Présage on this topic. The project of the company Le Présage is to open a restaurant that is innovative in many ways, one of which is to use solar energy as the main energy source for the kitchen. The photography on the right shows their current cooker. The main reflector focuses the sunlight towards the secondary reflector, which reflects it under a simple cast iron slab used by the chefs as a French cooktop. Unlike a plancha, a French cooktop is used with pots and pans, and its surface temperature is not homogeneous. In restaurants, chefs are used to play with that. They grill their vegetables and meat in the middle and let their sauce simmer on the side. The main objective of the Présage is to serve about 50 customers every lunchtime and some evening all along the year. For that, they need to have a well-working solar French cooktop. Its temperature must range from approximately 400 degrees on the middle to 100 degrees at the edges. Moreover, it must be able to deliver a thermal power bigger than 1 kilowatt and must be usable during opening hours. Finally, the solar cooktop must be installed inside the building. The members of Le Présage have also set themselves the additional constraints of maintaining the original spirit of the project. To build something that is useful, this is something to recall because it's not as obvious as it seems today. Accessible in the sense that people should be able to understand, build, and repair the system with common materials and techniques, and above all, sustainable. My PhD thesis is part of this big project. It is entitled Design of Restaurant Optimized for Solar Cooking and mainly deals with the solar cooker described just before. To sum up, I have to describe and model it, measure its performance, and propose thermal and optical improvements. I will also investigate the possibility of adding a heat storage, and I should finish with the modeling and study of the overall performance of the restaurant. Today, I will only talk about the second item, the measure of performance. For the purpose of our study, we built an experimental bench similar to the Présage cooker. It consists of a Scheffler reflector of 8 square meters, equipped with an automatic sun tracking system, a cast iron slab, a flat secondary reflector, a cast iron slab, and a big cooking pot. In order to situate this system in relation to the literature, we have chosen to follow the test protocol defined by the ASAP standard. The experiment took place in Marseille on the 17th of December. The day was perfectly clear and sunny. With the average elevation angle of the sun and the inclination of the dish, we computed the intercept area and the standard load to use. As we could not put this amount of water in our pot, we arbitrarily chose to use a mass of 22 kilograms of water instead. I will come back to this detail later. As specified by the standard, the ambient temperature and the water temperature were measured. The sensors were thermocouples type K, and the acquisition frequency was 1 Hz. In traditional box cookers, most of the energy captured is transferred to the water. In our case, the cooktop acts as an internal heat store. That's why 7 sensors were placed on the cooktop to measure its surface temperature. This makes it possible to estimate when the cast iron slab is storing or releasing energy. Ideally, the cooktop should have a constant temperature during the whole experiment in order to eliminate its influence on the measured power. The direct normal irradiance was measured by a weather station located nearby, whereas the wind speed was not measured. Nevertheless, the wind was almost absent because the day was calm and the experiment site is surrounded by buildings. The Scheffler reflector was oriented to the sun from 11:21 to 14:10 solar time. The graphic on the right shows the temperatures recorded. We can see that the bold blue curve, representing the water temperature, rises smoothly from 20 degrees to 95 degrees, whereas the red bold curve, representing the air temperature, remains around 16 degrees with a small noise. The other curves represent the temperature of the cooktop. The peak observed at the red and yellow curve is due to an untimely stop of the sun tracking system. This stop led to a small shift of the sunspot under the cooktop to the right of the diagram. Fortunately, the stop was short and the rest of the system was not much affected. As explained before, in order to reduce the influence of the heat storage in the cooktop on the results, we have chosen to calculate the standard power only over the selected period. Over this period, the average ambient temperature was 16 degrees. This is slightly below the range indicated by the standard, from 20 to 35 degrees. And it has had a consequence that I will explain right after. The average irradiance was 794 watt per square meter. So it's inside the range of the standard. And there was nothing to report about the wind. Now comes the results. The temperature difference between the water and the air is noted as TD. PS is the standard power, and R square is the determination coefficient obtained thanks to the linear regression. Here, this coefficient qualifies the proportion of the variation of the standard power predictable from the temperature difference. R square tends towards 1 if the prediction is perfect, and towards 0 if the prediction is not possible at all. The linear regression gives the red curve and this equation. We can already note that the experimental points clearly show a trend, but also that they are somewhat scattered around the trend line. This fact is reflected in the value of R square, which is above the limit value defined by the standard, but still far from 1. Another justification for this value of R square is the low ambient temperature. Indeed, the observed phenomenon is linear as long as the temperature difference remains small. We can clearly see the experimental points dropping where the temperature difference exceeds 75 degrees. That's why the standard advice is to have an ambient temperature higher than 20 degrees. It limits the temperature difference to 75 degrees. Finally, the standard power found for a temperature difference of 50 degrees is 628 watts. The results found are a bit disappointing. We had a reflector aperture of about 6.9 square meters, combined with a standard irradiance of 700 watt per square meter. So the solar power collected by the main reflector was about 4.8 kilowatts. And the equation says that the power supplied by the cooker goes from nearly 1 kilowatt when the pot content at ambient temperature, when the pot content is at ambient temperature, to 500 watt when the temperature difference is 70 degrees. Most of the energy collected never reaches the pot. We already have some explanation about that. First, the Scheffler reflector is made of numerous small mirrors fixed on rails. Although they seem small, these rails could still count for 25% of the surface of the dish. Then there are optical losses due to misalignment of the small mirrors. We can see it there. Of the platagonal mirror. Some rays pass above, other below. Lastly, the French cooktop is intrinsically anti-thermodynamic. This is a thing that only wants to give its energy to its environment. We also identified sources of error. Because this work is in progress, thermocouples have not been yet calibrated. The uncertainty of the temperature difference is plus or minus 3.5 degrees. For the same reason, the results relate to only one experiment. Moreover, the lid of the pot was not sealed and the evaporated water was neglected compared to the total mass of water. However, some elements of the standard raise questions. Is the quantity of water adapted for testing concentrating type cookers? We should have released the test with nearly 50 kilograms of water. While covering the cooktop of pots, we would reduce the losses and collect more energy. So, should we seek to assess the total power supply by the cooktop? It could make a big difference. And what about a system integrating a heat storage? Should it be preheated? As perspective, we need first to complete and enrich the present work, looking for answers to the previous questions. Then two main ideas emerge. The first one is to look for ways to improve the system. It means that we have to solve the challenge of the flat secondary reflector, which lets light pass below and above, and to reduce optical losses due to misalignment. To this end, non-imaging optic could be reuseful. It also means that we should reduce the thermal losses. Some ideas like adding a window behind, using a selective paint, or focusing the light on a smaller area would reduce losses on the underside. For the top, it's more complicated since we need to keep an interface compatible with the kitchen. The second idea is to improve our instrumentation. We are thinking to make measures using an infrared camera and inverse methods. We have already worked on a simplified case that you can see on the right, and we have now to implement it on our test bench. I thank you for listening my presentation, and I will be happy to answer to your question. Obrigado.